We'll start the story by journeying to the cosmos. Please join me in welcoming our first speaker, Shashank.
Okay, good evening, everyone. Can you hear me? Thank you all for attending on this lovely Thursday evening. My name is Shashank. I am a PhD student here at Yale's astronomy department, and I'm hopefully going to convince you that one of the answers to the question, where do we come from, is stars. So, as Stas mentioned, the underlying theme of today's talk is all about where did we come from and how are we engaging with the world around us. And of course, there are many, many different layers to this question. At the most fundamental level, we all know we came from our parents. If we now trace back our ancestry over the course of millions of years, then we're going to see the evolution of the human race itself as we evolved from primates. And then if we go back even further, that's when we would see the emergence of life itself here on this little blue planet. And we know that the Earth formed 4.5 billion years ago, and it's only one of 8 other planets in our solar system, which itself is only one of hundreds of billions of stars in the Milky Way galaxy. And our galaxy is only one among countless other galaxies in the entire universe. So this question has many different layers to it. And as an astronomer, I focus on the largest scales. So mostly these 3 bottom panels here. And let's start our journey. Let's start our journey by going back in time about 13.7 billion years ago. And that is when we would see the emergence of the universe itself, the Big Bang. So the Big Bang is actually a terrible, terrible misnomer because when I hear the words Big Bang, I think of a massive explosion, right? But it turns out the Big Bang was not big, and it wasn't a bang. So it wasn't an explosion in space, but rather the start of space and time itself. If we use Einstein's equations and follow the math and trace the math back 13.5 billion years ago, we would find that the universe began as a single dense point in space and time. And at the Big Bang, that is when space and time itself began. So there's very little that we actually know about the Big Bang itself. But what we do know is that shortly after the Big Bang, the universe looked very different than it does today. After the Big Bang, the universe consisted of about 75% hydrogen and 25% helium. And everything else, all of the other elements of the periodic table, simply did not exist after the Big Bang. Now, compare this to the chemical composition of the Earth. We know that the Earth is made up of a bunch of other elements. We have oxygen, we have silicon, we have iron, aluminum, all of these other elements. And especially if you look at the composition of life itself, life is made up of oxygen and carbon and all of these other elements, which simply did not exist after the Big Bang. So, how did we get here? Well, let's continue our journey now. If we now forward in time for about a couple 100 million years after the Big Bang, that is when the first stars in the universe began to emerge. Star formation is a very complex process, and we are still working on understanding it. But the basic principle is that stars form from the collapse of clouds of gas. So, using computer simulations, scientists are able to trace to understand how stars form from these clouds of gas. So, here is one such simulation. We're going to zoom in on this cloud, and the simulation occurs over the course of millions of years. So, we're quite literally witnessing millions of years go by in just a few seconds. And what we see in the simulation is that gravity is what is ultimately bringing these certain regions together and collapsing them, which eventually leads to the formation of stars. So fundamental force which ultimately leads to star formation is gravity, and we can see in the simulation here the certain bright spots are where the regions of star formation occurs, the first stars in the universe. In fact, we can see this process occurring in real time if you just go outside tonight and look up at the sky. So you might recognize this constellation. It's one of the most famous constellations in the sky. This is Orion. Easily recognizable by these three stars in a straight line. That is Orion's belt. Orion is a winter constellation only, and we're just about at the end of winter, so we can only see it for a few more weeks. So make sure to take a look at it before Orion disappears. You have to look towards the west, the southwest tonight. And Orion, the most famous part of Orion is Orion's belt, of course, but right underneath it, we see these three other objects. And one of these is not a star, it's a nebula. It's one of these clouds of gas that is actively forming stars as we speak. So we are quite literally witnessing the birth of stars. This is a stellar nursery. And of course, this process occurs over the course of millions of years. But if we look at the Orion Nebula through a telescope, we can see this process occurring in real time. The first stars that formed in our universe are called POP3 stars, population 3 stars, and they're actually very different from the properties of our sun. Our sun is very, very massive. It's over 4,000 billion pounds, which seems like a really, really massive object, right? But the POP3 stars were hundreds of times more massive than our sun. Our sun is very large. It's over 1 million miles in diameter. But the POP3 stars were tens of times larger than this. The sun has a surface temperature of about 10,000 degrees Fahrenheit, whereas the POP3 stars were much hotter than this. But the one thing that the sun does have going for it is that it has a lifetime of about 10 billion years, whereas the POP3 stars have a lifetime of only a few million years, which seems like a really long time, right? But if you look at this in the grand scheme of things over cosmic times, this is just a tiny speck. So there is a lot of truth to the saying that the brightest stars burn out the fastest. Now, what exactly do I mean by the lifetime of a star? A star's entire life is a continuous tug of war between pressure and gravity. Gravity wants to collapse everything inward. It wants to bring everything close together. And this is resisted by the outward force of pressure. This pressure comes from the core of a star, where the temperatures are so high that hydrogen atoms can smash together with enough energy to fuse together and form helium atoms. So this is the process of nuclear fusion. And you might have heard of nuclear fusion in the context of renewable energy and solving the world's energy crisis. And the reason why it's so hard to solve is because we need to somehow simulate the conditions, the temperatures that are found in the cores of stars here on Earth, which is a really, really hard task. Some of the best minds in our planet are working on this, and we have made a lot of progress over the past few decades, but we're just simply not there yet. But coming back to stars, hydrogen is the ultimate fuel for stars. So as long as a star has enough fuel in the form of hydrogen, it can survive against gravity. But what happens when it starts to run out? And here we need to distinguish between low mass stars and high mass stars. So our sun is very massive, but still on the cosmic scale of things, it's considered a low mass star. Once a low mass star runs out of hydrogen, it's going to burn helium instead into other elements like carbon and oxygen. This is what we call as the red giant phase. Once a red giant completely runs out of fuel, it's going to expand. The outer layers are going to expand and wither away into space. This is called a planetary nebula, and the core is going to form a white dwarf. And this is ultimately the path that our sun is going to follow once it runs out of fuel. But this isn't going to happen for at least another 4 to 5 billion years, so we can all sleep soundly tonight. On the other hand, high mass stars follow a different trajectory. Once a high mass star runs out of fuel, it's going to become a red supergiant. And again, we can see a red supergiant tonight if you look at Orion. This is why Orion is my favorite constellation. There's just so much going on here. We just saw Orion's nebula, and now if you turn our attention to the top left here, we would find a very bright, very red star, and this is the star Betelgeuse, which is a red supergiant star. If Betelgeuse were at the center of our solar system, then all four of the inner planets, Mercury, Venus, Earth, and Mars, would be engulfed by Betelgeuse. It's a very massive star, and it's not going to be around for very long because any moment now, Betelgeuse is going to completely run out of fuel and explode in one of the most massive explosions in the universe called a supernova. Um, but of course, this could happen anytime between now and 100,000 years from now. But one can hope, right? Supernova are some of the most massive, violent explosions in the universe. When Betelgeuse goes supernova, it's going to be as bright as the full moon, but we are very safe from it, so we don't have to worry about anything. It's just going to look really cool. And finally, the core of a massive star is going to contract and form either a neutron star or a black hole, which are really, really cool. But but I'm not going to talk about them here. So feel free to ask me later on. Supernova are really important for the evolution of the universe because all of these elements that were created in the course of stars, like carbon and oxygen, are now flung out into space by these explosions. So we can quite literally think of supernova as cosmic fertilizers. They are releasing all of these elements that are churned out in the course of stars out into space. And these elements make their way into the next generation of stars. So the story that emerges is that the first generation of stars in the universe, called Pop 3 stars, they didn't live for very long, so they're not really around anymore. They're mostly extinct. But once they went supernova, these elements found their way into the next generation of stars, called Pop 2 stars. And some of these still exist, but they're still very far away. And some of these Pop 2 stars went to supernova to create the current generation of stars, like our sun. And so we can see that there's a very nice, very elegant cycle of life and death occurring on the grandest scale. So coming back to the periodic table here, you might recognize this from high school. And the only thing I want to point out is that the first two elements, hydrogen and helium, they were formed all the way at the Big Bang. But all of these other elements, which were quite essential for life as we know it, were actually manufactured in the course of stars. Now, of course, there's one particular star that we all care about, and that is our sun. As with every other star, our sun formed from a collapsing cloud of gas and dust. So here is a computer simulation of how we think the sun formed. And what I want you to pay attention to is most of this material fell into the center. That's what led to the star formation, but not all of it. Some of it was some of this leftover material went around orbiting the sun, and this is what we call the protoplanetary disk. And as the name suggests, the protoplanetary disk is ultimately what gave rise to the rest of the solar system, like all of our planets. So you can see in the simulation that the planets of our solar system came to be from the protoplanetary disk. So everything in the solar system, other than the sun, the planets, the asteroids, the comets, they are quite literally leftover material from our solar system's formation, which quite didn't make its way to the center. And again, we can see this happening in real time. So using some of our best telescopes, scientists have looked into into other stars, and we have found protoplanetary disks. These are quite literally these are other solar systems that are in the process of forming. And all of these gaps or rings that we see in these images represent other planets that are actively being formed as we speak. Now, In addition to all of the planets, our planet Earth has a companion, the Moon. So for a long time, we didn't know how the Moon got here, and right now, our best theory is that the Moon came to be because of a collision between the early Earth and another planet. So here, this other planet is called Theia, and we're going to see a computer simulation of Theia as it collided into Earth, resulting in a very massive, very violent collision between these two planets. And ultimately, some of this leftover material was flung out into space and left orbiting around the Earth. And this is ultimately what became the moon. So, our moon is the result of an early collision between another planet very early on in the solar system's history. Now, this happened 4.5 billion years ago, and thankfully, nothing like this has happened since then, because that would be disastrous for life on Earth, right? And the reason for this is that some of the other planets of our solar system actually flung out anything which could have collided into Earth. So here is a simulation of how we think our solar system emerged, and we're speeding up time. So we're witnessing millions of years go by every second. And what we see is that because of some of the other planets in our solar system, the asteroids and other smaller comets that could have collided into the Earth are flung away. They're slingshotted away due to some of our gentle giant planets like Jupiter and Saturn. If it wasn't for Jupiter, our planet would have been subject to a much more violent history where we would have witnessed many, many more asteroid and comet strikes. But thanks to Jupiter and Saturn, they have cleared the way such that we have now entered a much calmer, much quieter place in our solar system's history, and we need this calmness for life to ultimately emerge. So this is we have to thank Jupiter for resulting in this calm and quiet period. And you can see at the end of the simulation, most of the asteroids that existed have been cleared away. The last thing I'm going to talk about is the ultimate emergence of life here on Earth. The early Earth was very different from how it looks today. The temperatures were much hotter, so the oceans were quite literally boiling. There was a lot more volcanic activity going on and a lot more lightning strikes. So this it seems like a very scary place to live, and you'd be right. Except that these conditions were necessary, in fact, for life to come about. So in our atmosphere, there are all these gases like oxygen and nitrogen. Our oceans had water. The volcanoes emitted copious amounts of methane and ammonia, and lightning is going to play a very crucial role. So all of these building blocks existed in the early Earth, but how did it get from here to life as we know it? So this was the subject of a very famous experiment called the Urey-Miller experiment, where these two scientists tried to simulate the conditions of the early Earth. They took they took a test tube and put in gases like oxygen, nitrogen, methane, and heated it up to simulate the early hot Earth, and then passed lightning through it, electricity through it, which simulates lightning strikes. And what they found is that just a simple setup led to the emergence of the building blocks of life in the form of amino acids. Kriza is going to tell us more about amino acids. But we can see here that the building blocks of life emerged because of the natural conditions on Earth. So as I reach the end of my talk, I just want to zoom out here and just review everything we learned. We think that the universe itself began in not a massive explosion, but we call it as the Big Bang, about 13.5 billion years ago. This soon after the first stars in the universe emerged. They didn't live for very long. They went supernova, leading to the next generation of stars, which themselves went supernova, leading to the current generation of stars. And like our sun. But not all of the material went into forming the sun. Some of it was left over, and that is ultimately what gave rise to the planets as we see today. And one of these little planets hosts life as we know it. So whenever we look up into the night sky, I like to think, I like to feel a sense of appreciation and a sense of awe that so many cosmic events happen to lead us to where we are today. When we look up at my favorite constellation, Orion, we can see Orion's Nebula, which is a region where stars are actively being born as we speak. As well as Betelgeuse, which is a star that has nearly reached the end of its life and is going to go supernova, and in doing so, fertilize the rest of the universe with all of the elements that are necessary for life. Whenever we look up at the full moon, it's going to be full moon in about 10 days or so, I think. The moon reflects our history as the Earth underwent a violent collision, giving rise to this beautiful satellite that orbits us. And of course, whenever we are stuck inside and stuck indoors during a thunderstorm, lightning was a very crucial ingredient in forming the building blocks of life by combining together gases to form amino acids. So here I want to end with this beautiful quote by Carl Sagan that we are all made up of star stuff. So thank you very much. And now I will pass it over to Krista, and I'll take any questions later on. Yeah, we'll take questions together at the end of our Kriza's talk as well. So thank you very much.
Great. Hi, everyone. My name is Kriza. As Shashank said, we'll take questions for both of our talks at the end, but please hold on to your question. So I'm similarly going to talk about the question of where do we come from, but I propose that my answer to this question is we come from food. And so Shashank's talk focused a lot on how there was this really efficient process of stars being born, stars dying, and then the leftover material being used to then build new elements and contribute to the next generation of stars. So it's this really efficient process of using material from one generation to build the next. And I think food can do this for us when we think about zooming in on where we come from here on Earth. So food fuels us in life as we grow, and to get food, inevitably involves the process of death through either the plants that we're eating or the animals that we're eating. And so we'll talk a little bit about like where we're getting our food from and how that helps connect us, or in some cases fails to connect us to the rest of the natural world. And then we'll go into how worms can help us reconnect a little bit. So just to start, when we think about where we're getting our food from in today's society, if you live, in a city, a town, somewhere with lots of people, good support, most of us are getting our food from grocery stores, right? Like we're not necessarily growing our own produce. We're not farming our own animals for the most part. Although if you do, like, please share at the end. I'm super curious to hear. But most of us are still going to the grocery store for all of our basic necessities. And it's really convenient for us so we can focus our lives on doing a lot of other things that bring us joy rather than all of us striving to get enough food. And then when we prepare this food, we eat it. Inevitably, there's going to be either leftover food that might go bad or byproducts from cooking the food that we don't typically eat, right? Like onion skins, banana peels, citrus peels. So there's a good amount of food that ends up in landfills, right? We take it out in the bin when the garbage truck comes pick it up. And there's a statistic that around 50% of all the mass in the landfills are actually organic materials. So basically food and food-related waste. And this is a lot of material that's going into the environment. And this is actually not the most efficient way to deal with organic waste. And we can turn to what's happening in nature to figure out like what is the most efficient way, right? Like if we can get energy from food, what about all this extra food waste we're throwing away? There should be energy that we can harvest in some other way, even if we're not eating it. And so if we look at nature, we can think about how all the organisms interact and share energy with one another through something called a food web. And so we'll start with the most basic component of the food web. So our plants are producers of energy. These guys get their energy from the sun. And so these are your trees, your crops, your grass. These things are eaten by herbivores like the very hungry caterpillar. And so I'm drawing energy in this little green hexagon over here. And these herbivores are then eaten and share their energy with other animals like fish, birds, and then those are eaten by other animals and so on and so forth. And so when we think about what happens to the energy here, it might stop at the fox. But what happens when the fox or, any other carnivore dies is that the body gets broken down by numerous creatures, including fruit flies. So normally we don't like to think of fruit flies as being helpful because if they're in your fruit in your house, that means you probably don't want to eat it. So fruit flies, worms, and then also big things that we consider carnivores, like bears and wolves and dogs. These guys will also eat a lot of unwanted things, like especially for our pet animals. We don't want them putting some things in their mouth that they do when you take them on a walk. And so these guys will eat the decaying matter from dying creatures. And then inevitably, all living things produce their own forms of waste. And these have to get further broken down by things that we can't see with the naked eye. So bacteria, yeasts, and then also mushrooms, or like more broadly fungus. And so this last bucket of organisms is really important for taking all of the organic matter from any creature in this cycle and converting it back into a form that can be taken up and used to fuel the trees and the plants. So it closes the circle to really get all the nutrients back into the system. And so with our human food waste going into the landfill, we're really separating out, we're really like plugging into the normal food web kind of at the top of the food chain, right? Like nothing's really eating us and we're eating everything else. But inevitably, even humans will go on to become worm food. And when all of our food waste is going into the landfills, we're pulling out that energy away from ways that it could be better returned to the environment. So you imagine if you like toss a banana peel into a forest, like that is food that can be used to feed, I don't know, the ants, the flies, and return all of those nutrients back eventually to get to the trees. And so when we think about how can we better deal with our organic waste so it's not just sitting around in a landfill, we can actually really look at what nature does and try to adapt that to our waste practices. Because I think there's benefits to having, a trash pickup day so that trash isn't on the streets. Like it's good for public health, but we can maybe be more efficient in how we're dealing with some of that waste. And so just to go into a little bit more about what these organisms are that I've circled here in green, we'll talk about how these two groups of animals, scavengers versus decomposers, help digest organic waste. And we can think about it in terms of our own body's way of digesting food. And so the way that we digest food is broken into two main ways. The first you might be familiar with is chewing. So this is considered mechanical digestion. It's the process of breaking big pieces of food down into smaller pieces of food, and this helps it go down into your stomach, and it helps get everything digested quicker. So this is all just breaking things up into smaller pieces. The second important part about digestion is this process called chemical digestion. So if you've ever taken like a cracker and just let it sit in your mouth without chewing it, you'll notice that it'll get soft and sometimes it'll even taste sweeter after a while from your saliva just breaking it down. And so this is happening because in your mouth there's specialized chemicals in your saliva that will actually start the process of converting the stuff that's in the food into different types of nutrients that your body can then absorb. And so in nature, the bacteria and the yeast and the fungi that live in the environment, they're doing this on the larger scale for all of the nutrients that make it into the soil. And they're converting these nutrients into formats that plants and trees can use more efficiently. And so these two buckets of organisms are really important for recycling organic waste. And so if we're trying to recapitulate this using, human technology, we're still going to want to keep the bacteria and the yeast around. Like, these guys are really key in getting that last chain of recycling back into something the producers can use. And so just like us, some bacteria like to use oxygen, and they need oxygen to grow. And so we can divide the types of organic waste recycling into anaerobic digestion. So this is bacteria that don't need oxygen. And then compare that to aerobic digestion, or what I'll just refer to as composting for the rest of the talk. And this is where we're utilizing the bacteria that like oxygen and need oxygen. And so these two things have different applications depending on, the scale of how much organic waste we want to recycle. So starting with the anaerobic digestion, this can take almost any form of organic waste. So you can take manure from the agricultural industry, you can take wastewater from our sewage industry, food waste, and then any other organic byproducts from like beer brewing or getting oil. All of these byproducts can go into an anaerobic digestion system. And so this is usually some type of enclosed container. That's really all it is, where you put all these things in, and then maybe you'll have some starter bacteria. And if you just let this sit, all the bacteria will take up all the nutrients from all of these different things that you've put in, and they'll create two main byproducts. One, they'll create something that can be used as fertilizer, and they'll also create a lot of gas, or what we'll call biogases. So these are usually pretty smelly gases, and they're flammable. So usually that's bad. But if you're able to harvest this and do it in a controlled way, you can actually use this gas for fuel. And so in this process of breaking down all of these large-scale industrial waste, you're able to actually get energy we can then convert into like electricity, and get fertilizer to grow a next generation of crops. And so I have an example here from this small town in Cortland, or in New York, that has tried to do this for a dairy industry that they have over there. And so this is pretty useful for large scale industry, just because it can handle a lot of types of waste that smaller compost systems aren't really good at handling. And we don't normally like to do anaerobic digestion on smaller scales just because of the gases that are produced. They can be pretty smelly. Okay, so then another way that you can kind of implement organic waste recycling is through composting. And so different cities will have different scales of trying to implement this. So we're coming to you from New Haven. And here on the left, I'm showing this trash can that was designed for collecting compost through the city. And so there are a couple of these bins placed downtown in the streets that residents could just come and drop off organic waste. This was a pilot program, so I don't think they're offering this anymore, but the city did try it out for a couple of years to collect people's food waste. Alternatively, in the city of New Haven, we have a private company that will help you compost your food waste. So if you sign up and pay like a monthly subscription fee, you collect your food waste in a separate bin, but put it out on the curb just like, your other recycling, your normal trash. And then once a week, folks from this company will bike around with this cart of plastic bins. Like, this image here is real. You can see these people biking around New Haven. And so they'll collect all the food waste and then bring it to their site where they'll actually compost it and turn it into fertilizer. And then you can opt in to receive the end products of that compost yourself, or donate it to a local community farm. So this is a really nice way to kind of contribute to the system and then also benefit directly from the organic waste recycling happening. And so these options can usually vary depending on where you're coming from. And so if you're still interested in dealing more efficiently with your organic waste and getting something more out of it, you can actually compost at home. And there's a bunch of different ways to do this that, you might pick one or the other depending on like where you're living, how much yard space you have. But when people think of composting, I think usually it can be as simple as like two side-by-side piles of organic waste and yard waste. But there's also new countertop options available where you can buy these bins off of like Amazon. I think they come with like a shredder function to make your food waste, break it down into smaller pieces. And I'm not entirely sure how they work, so if anyone ends up buying one, let me know. But they are available on Amazon that will just sit, inside your house, no smells, sit on your counter for really convenient recycling. And then there's another option that you can actually purchase for like an outdoor garden that's more enclosed compared to these two separate piles up here. And then my personal favorite way of composting is using compost worms. And in the next slide, I'll talk about the difference between regular composting and then worm composting. So between these two methods of composting, what's shared is that we're still using aerobic bacteria. So we still have bacteria that need oxygen to grow and do their job in breaking down all the nutrients. The differences with regular composting is that it's something that is typically done outside. And because you only have bacteria involved, you're really dependent on the weather. So bacteria will only be super active in warmer temperatures, like from spring to fall. And then they'll go to sleep in the winter. And so you won't really get any composting done then. And so this is a process that's pretty slow and it's weather dependent. On the flip side, worm composting is really flexible. So worms will be happier at a wider range of temperatures. And you can do this inside your house without, attracting pests or creating smells. And then, your home is a little bit more of a controlled temperature environment. So you can definitely be composting year round. And then because these are using bacteria that are that want oxygen for regular composting, because you don't have worms in there, you need to manually mix in oxygen to the pile every once in a while. And so this is kind of like if you're beating air into eggs for a cake. Every once a month or once every 2 weeks, you need to manually churn your pile of organic waste. And depending on how big your pile can be, this can get pretty heavy. In comparison, worms are living in the compost. They're swimming through it to get to the next batch of food. And so they're poking holes in the existing pile of compost and introducing oxygen for you. So once you put your food in, that's really all it takes to keep your compost bin going. Okay, so how can you actually make a worm compost bin at home? Because it's super, super easy. You can do it in as small of a bin as you want or as big of a bin as you want, depending on how much food waste you produce. And so you can go and buy a plastic bin from the Container Store or from Walmart for, I don't know, Walmart would be $2. And you can poke some holes in it so that you can get oxygen going into the bin for your worms, or you can just kind of leave the lid cracked. And so this will be your worm's home, and it can be as big or small as you want it to be. When you're starting off your worm bin, you want to add a little bit of potting soil just because worms are not going to be happy swimming around just in plastic. So you'll start out with just any kind of potting soil. You'll add a little bit of bedding, so usually in the form of newspapers or old cardboard, like cut up cardboard. And this just helps to normalize the moisture in the environment. It gives a little bit of food and bedding for the worms. And then you'll give them water. Worms they like the soil to be pretty moist, not entirely dry, but not soaking wet. And if you'll notice, when it's raining outside, the worms that crawl up are trying to escape the soil that's getting really, really flooded during rain. And so worms like a very specific amount of moisture. And then the last thing you'll need is just one more layer of newspaper on top of this entire thing. And this helps just keep the moisture in the soil so it's not evaporating too quickly. And then you can get your worms from a local bait shop. You can buy them online. You don't need a ton to start with, depending on how much food waste you produce. And the worms, if they're happy, they'll also continue to reproduce throughout this process. So it's kind of like you buy them once and then you don't have to buy them again. Now, the most important part about maintaining a worm bin and making sure your worms are happy, like with any other pet, is you want to think about what you're feeding them. And so keeping your worm bin happy and making sure that things are breaking down correctly relies on a balance of the worms doing their mechanical digestion process of the food scraps you're giving them, and then making sure that you do still have the bacteria, the aerobic bacteria that you want to finish that final step in the process. And we can think about what food we give worms by thinking about what food we feed ourselves. And so we want high carbon food for the worms, and we want to limit the amount of nitrogen. And to figure out like where do these things come from, we can think about what goes on our own plate. So if you've heard the term of macromolecules floating around, like in the nutrition industry or like with your doctor, this is the idea that there's really three big buckets of food that we need in order to be healthy and have energy. And so the first bucket of food are the carbohydrates. So this is the hexagon that I was showing earlier that was demonstrating like energy passing between organisms. So carbohydrates really are a good source of energy for people. This is including pasta, rice, bread, but also fruits and vegetables. So a lot of things that have sugar in them, we can bucket as carbohydrates. The second macromolecule we think about is protein. So that's drawn as this little stick figure here. Most of our protein sources come from meat and dairy, and then you can think about like legumes, beans. Then there's a lot of like protein supplement options now, like protein drinks, protein shakes, etc. So that's our second big bucket for macromolecules. And then the third one is fats, which are important in our diet, but for a worm bin, they're a little bit too complicated. And so a good rule of thumb is just to not add extra fat to your worm bin. But focusing on carbohydrates and proteins, we can think about where carbon and nitrogen come from by looking at the cartoons that I've drawn here. So these are actually drawn to resemble what the actual chemical structure is of these macromolecules. And so what I've circled here at every point represents where different elements sit in a single unit of a carbohydrate. So carbohydrates are made up almost entirely of carbon. You can see all 6 of these points in the hexagon are carbon. And that's compared to protein, where this backbone here that I've circled with the 3 points does have 2 carbons, but it also has 1 nitrogen. And so when Shashank earlier mentioned that like one of the building blocks of life is amino acids, this stick figure here represents 1 amino acid. And then for a single protein out of the hundreds of proteins in your body, or hundreds of thousands of proteins in your body, a single protein can have like up to 300 amino acids. So you can imagine how nitrogen kind of adds up really quickly when we think about these building blocks making up proteins, making up a body. And so our nitrogen sources are normally we're thinking about protein, whereas our carbon sources, we're thinking about carbohydrates and fruits and vegetables, especially when we think about food waste. And so in terms of the food that you're giving your worms, you really want to emphasize fruit and vegetable scraps to get that carbon source, and limit meat in your food bins, in your worm bins. And then the last piece of kind of like a good guideline for feeding your worms is just thinking about the environment. So worms both live and eat in their environment, right? They're swimming around in the food that you're putting in for them. And so similar to us, they don't like a ton of acidity. So for us, that's things that give us like reflux. And so you also want to limit the citrus peels that you put in and coffee grounds that you put into your worm bin. And then, if you follow these general guidelines, you keep an eye on the moisture levels in your worm bin. You'll feed your worms like once every 2 weeks or so, and then you'll get usable compost within the next 2 weeks. So it happens pretty quickly. And so just some of the end products from worm compost are obviously the compost itself that you can use for your garden. You'll get happy worms that make more happy worms. And if you're a fisher, you can actually use these as bait if you want to. And if you don't want to be using the actual soil for your plants, you can also kind of make your own liquid fertilizer by making something called worm tea, which is basically where you take the soil and you steep it in some water, and that'll extract all those good nutrients that the worms and bacteria have helped recycle into the actual water, and then you can strain out the solid parts and then use the rest to water your plants. And you can also buy worm tea online, but just keep an eye out for how they make them, and I think you can like fact check people on what they're selling as worm tea. So just wrapping up the talk, hopefully I gave you some ideas of what to do with organic waste, or you can look into citywide initiatives that might be around where you guys are, or even make your own worm bin. And so a little bit of homework for you is if you're interested in a worm bin, or you're just more interested in worms in general. We're hitting like the rainy spring season, so the next time it rains, you can look down at the ground and appreciate the worms that are coming out and fighting for their lives. And I think Shashank gave you some homework to enjoy the Orion constellation in the last few weeks that we have it for the winter season. And that's it for our talk. So with that, we'll take any questions, but thanks for your attention. Oh, there's a hand.
Wait. Sweet.
Would you like me to ask my question, or do you want to wait?
Yeah, go for it.
Okay, I have one for each of the speakers. I had a question on what is the name of the planet that collided with Earth? It sounded like Pia or something like that. What's the name of that planet?
Thea, like Thea, I think.
Thea. Okay, thank you. That's what I wanted.
Yeah,
to
it was about the size of Mars. At least that's what we think.
Okay. Okay, thank you, Thea. And the second question was for Kriza. I'm sorry, I can't pronounce your name.
You got it.
Sorry.
Kriza, you got
Kriza.
it. Yeah.
And at the very end, was it that if you're going to do a worm bin at home, do you water it every 2 weeks or feed it every 2 weeks? I missed that one piece at the very end.
Oh, that's a good question. Yeah. So you want to check on them around every 2 weeks. The frequency of feeding really depends on how much food waste you're producing.
Okay.
And how many worms you have. So like a pound of worms will process, I don't remember the exact metric, but like a certain amount of food waste every week. And so you can kind of figure out how often you need to check them based off of how much food waste you're giving them. So if you're generating less food waste, you probably want to feed them more frequently as you get more waste. But you're kind of balancing like the worm's ability to do their job in time and like eat enough regularly compared to all the other bacteria or molds that might want to also like take advantage of the food that you're putting in. And so usually it's pretty flexible, but I think every 2 weeks, like the worms will be okay if they're hungry for a bit, and if you don't get around to feeding them. Go ahead.
I had a question because I tried this quite a few years ago in New Hampshire, and I remember with the newspaper. Do you change that newspaper on top? I remember that the newspaper got very funky. It didn't really work out. My friend was doing it for me on my porch, but it didn't take too well. So you don't change the newspaper ever. You just leave it there, and you put the food on top?
So there's kind of two places where the newspaper will go. You'll in terms of like what I call the bedding, it'll be more shredded newspaper, and you can just tear it up manually. They don't have to be super small. And so it helps to soak all the newspaper in water for just a couple of seconds, like saturate the newspaper in water. Because the newspaper will serve as like a source for holding onto water when things get too dry. And then also it's an additional carbon source for the worms. And so eventually, like, it will break down with the worms and bacteria doing their jobs in the bin. And so I've never had to take newspaper out. Occasionally, once you stop seeing big chunks of newspaper, then you should be adding more. And then there's like a top layer of newspaper that goes in just to hold on to the humidity. And that one I will water. So either I'll take it out and soak it in water and then put it back on, and that'll kind of just set a good like humidity source for at least a week or two until the next time I check on them.
Well, the food goes underneath the top layer of newspaper. That's another question. Or do you just?
Yeah.
Oh, okay.
Yeah. So the top layer is like a blanket over the entire thing, especially because we're not usually putting a lid, like completely closing it so that you can let oxygen come in. But like the worms will find the food no matter where you put it, but I like to sometimes just bury it because I'm always paranoid that like other like molds might grow. But I've also seen people who do it just right on top of the soil level and then underneath the newspaper blanket. And
Okay,
and
so
that speaks to what they're about.
underneath the blanket when you feed them. Okay,
Mhm.
thank you very much, both of you. I love this talk from both of you. Thank you so much.
Yeah, good luck with
Thank you.
the worm bin, hopefully.
Yeah.
No, I think Albert has had a hand up for a bit.
Oh, good. Because I can't see myself. My questions are about gravity. And it's a huge topic, I know. First question, I'll say them three and you answer what you can, what you want to. Was gravity around at the Big Bang? And okay,
go ahead.
Well,
Yeah, gravity was definitely around at the Big Bang. What it is, gravity is the dominant force at large scales. It's ultimately what shapes galaxies and galaxy clusters and solar systems together. But if you compare it to all of the other forces like electricity and the nuclear force, gravity is much weaker than the other forces. So at the Big Bang itself, gravity was still there, but the other forces were much stronger than gravity. And it's only after the universe expanded that the other forces became relatively weaker and gravity was able to dominate over everything else.
okay. Do we know what gravity is?
That's a very good question that a lot of people are working on this. We still don't have a complete picture about what exactly gravity is.
Okay.
Einstein gave us the biggest leap that we had in a long time with his general theory of relativity. But even ever since then, we haven't made that many leaps since then. Yeah.
Then last one, thank you very much. Last one, there was a lot of talk a few years back about dark matter. It's now not being talked about so much. Is dark matter, you think, the answer or what?
So dark matter is very actively being researched upon. I myself work on dark matter, and I think the majority of the community agrees that dark matter does exist, but we can't see it. We can only detect its influence on the through the motion of stars in a galaxy. But there is a lot that we still don't understand. We understand some of the properties of dark matter, but we still have no idea what exactly it is.
And is this dark matter, and the last question, is this dark matter then the space in between physical entities like planets and so forth? Is it the space in between? Is that what we're talking about?
So you're correct. It is kind of like the space in between. But again, just like gravity, you need to really zoom out to large scales, to the scales of galaxies, and that's when the effects of dark matter become evident. On the scales of planets, and so even on the scales of our entire solar system, it's very, very subdominant, and that's why it's so hard for us to detect, because there's just so little of it, and you really need to zoom out to the scales of galaxies for dark matter to become dominant enough to have a noticeable effect.
Thank you very much.
John, do you have a question?
Yes, I have one question for each of our guests. Shashank, I would start with you, if I may.
Mm-hmm.
There are a lot of planets in the universe based on finding that there's at least one for every star, and there's a lot of stars. So that leads to this point that in 2023, we landed on Bennu, which was a traveling asteroid that came through our system. And we brought back some samples that contained DNA, all 4 amino acids of DNA. Does that kind of show us that there's life in the universe, maybe in many more places than we think?
Yeah, so that's again, that's a really good question. I think that's a $1 trillion question, really. If we did unambiguously detect life on other planets, that would be that would have a lot of scientific but also social implications. It is a big leap from detecting amino acids to life. Just think about planet Earth. Earth formed 4.5 billion years ago, and I do believe that the formation of amino acids was pretty quick after that. But it still took billions of years until even just bacteria, single-celled organisms to arise, and then after that, it took billions of more years before multicellular organisms like us could arise. So. Yeah, it is. It is a big discovery that we found amino acids on Bennu, but it's not evidence yet that life exists. And there are a lot of people who are working on signatures of life, because planets, other solar systems, other planets are just so far away. There is not really any hope of ever just looking at a planet and seeing anything close to what we see in science fiction movies. And it's really the question is, what do we detect from another planet that would be unambiguous detection of life? I think that's still very much an open question. But yeah, I think a lot of astronomers, including me, are hopeful that there is life on other planets. But yeah, we're not really at the scientific at the point where we can make any scientific conclusions just yet.
Understood. Thank you very much.
Mm-hmm.
And for Kriza, is that
Yep.
Is that the way to say it? Thank you. In 1987, I know that's a long time ago, but there was a great article in the New York Times about a biochemist who had isolated a anaerobic bacteria that could create methane and break down solid matter very quickly. And it was very exciting to me to read about that. I was a major in biology and could follow the article, and it was a quite extensive article, and he proved his system. He isolated that bacteria and put it in a form that could be used in a sanitary treatment plant, and took 10,000 gallons a day for several years and broke it down quite successfully into methane, and then grew out plant material from the waters. And I thought, this is the beginning of something very big, and then it just disappeared. Do you have any idea what happened?
I thanks for sharing the story. I'm not too familiar with exactly what happened, but I would imagine, and I feel like you see similar things kind of across. So there's a lot of really specialized bacteria that can break down the very complicated waste products that we produce. So that's not just like food and things going into sewage, but even like plastics. There's so many different types of plastics. In theory, maybe there's one of like billions of types of bacteria that would be able to break down, one of the plastics that we produce. I think the hardest part, and the reason that usually these things don't take off, is that they're unfortunately maybe not the most financially like incentivized to implement it, depending on what existing wastewater treatment options are. And I can imagine that, like, I think bacteria can do really cool things, and we can use them to actually like improve human health. We can use them for processes like this. But I think the liability behind someone saying, hey, we're going to treat wastewater with bacteria, and then we recover some of that water for other purposes, I think there'd probably be a lot of like instinctive fear of what happens with that bacteria. Is it going to contaminate things? And I think especially like from the bioengineering field, you can do a lot of genetic modification of bacteria to make them more efficient at breaking things down. So people are doing this with bacteria to try to break down plastics. But I think, with the fear over genetically modified foods, I think it's probably something similar where there's a lot of like public public speaking and like public image work that needs to be done to show like safety, that not all bacteria are necessarily going to cause disease, and that like the genetic modifications that we might use to make them really helpful are safe. And honestly, like I think we still need to figure out how safe these things are, what effect they have on other organisms in the environment. So I think there's a lot of factors, but I hope that technology is being used somewhere, if not in the US. Kim has another question.
Yes, I do. And this is for the gentleman speaking about the planets. You know, when I hear about science research looking for life on other planets, it always, to me, seems to be looking for what we consider life here. And I just have a sense for some reason that other life forms may be also in other dimensions or energetically different from us, not necessarily how we think of life. And that's a question I have for him, if that gets looked at when you're checking out other planets or stars or whatever.
You're absolutely correct. Whenever we look at whenever we are talking about looking for life, almost always we are looking for life as we know it. There could totally be other forms of life that we have no idea about, and the thing is, we just have no idea what sort of signatures they would emit. What do we look for?
Right.
I think one of the key things that scientists look for now when they discover a new planet is there methane on this planet? Because methane is one of the gases that is primarily released by organic compounds or released by life. By decaying life, for example. So if you discover a planet with a lot of methane on it, that's it's not a smoking gun signature. Methane is also released in volcanoes, for example, but it is something that people take a closer look at and then look at other molecules. Okay, is there this other molecule on this planet? And that's, again, all of this is based on carbon-based life forms as we know it, as we understand.
Right.
But there could be life which is made up of something completely different, and we just have no idea what to look for.
Right. Some kind of other energy system, almost
Maybe.
electricity or something. Okay. Well, that's what I was curious, because I'm always kind of disappointed when they're looking for life forms. I'm like, well, maybe there's another life form that we just don't know. And we can't see even. Okay, thank you. This is wonderful talking from both of you.
Okay, well, if there are no more questions, I'd like to thank you both for very interesting presentations. And I think that we'd love to have you back again. So thank you to the Yale grad students for doing this for us. And we hope to have you back sometime again. Have a good night.
Thank
you so much for having us.
Thanks for all the questions. All right, have a good night, guys.